Hi, this is Professor Fernandez, and we are talking in this video about Module 2 in Lesson 5. So, Module 1 in this lesson was about multivariable functions, and we're now starting to get into some of the calculus of those functions. We're going to talk about limits in this video. The first thing I want to do is to remind you very quickly of the basic notions of limits from Calculus 1. So I'm going to draw here a function of one variable, y equals f of x. And we had this notion that at a specific c value, we wanted to investigate what y values the function approached. And if the y values approached the function L, the value L, as x tended to c, then we wrote limit as x approaches c of f of x equals L. Again, there's much more to this, much more detail to this. I just want to conjure up these memories of what you know from Calculus 1. The one detail that I do want to point out is that we had in Calculus 1 this notion that this was true if and only if the left and right-handed limits were equal to each other, equal to this same y value L, and each of these exists. Okay, so in other words, if I approach C from the left, I should get a number. It should be the same as if I approach C from the right. I should also get a number. It should be the same as L. It was under that condition that we said this so-called general limit existed and was equal to that common value of L. The situation gets a lot more difficult in 3 dimensions because for functions of 2 variables, we have many more than just 2 possible directions of approach. So let me just show you that visually. And this is what's really going to lead to lots of complications for us. But we'll resolve these in a minute. So let's say here is my surface. Here's my z equals f of x, y. Oops, f of x comma y. And then let's call this point a comma b in the domain of the function. Let's just suppose that f of a, b, the y value of the function, equals L. So here's the thing that you notice. There are so many ways that we could be on this surface z equals f of x, y and approach this L. We can come at it from this direction. We can kind of zoop around like this. Can come at it from over here. So the notions up here of approaching just from the left or from the right, and there only being 2 directions associated with the point C, approach from the left or approach from the right, those simplistic notions in single variable calculus are just no longer there for multivariable calculus. As this picture shows, we have so many ways to approach the point A, B, and the x-axis that translate to lots of different ways of approaching the y value f of a, b, if that exists. So that really just throws out the door a lot of what we knew about limits and makes us have to rethink what we are going to do to define limits in the function 2 variables case. Well, yes and no. We do have to rethink it in the sense that much of the discussion of limits in single variable calculus revolves around the type of approach, I should say, that I reviewed up here. So we talk about left and right limits, we talk about the limit laws, we talk about x approaching c, or f of x tending to L. We use words like that. There is a much more rigorous definition of the limit called the epsilon delta definition of the limit, which is actually what we need in the 3-dimensional and higher case to talk about limits. So that actually leads to this definition down here. However, because this definition is not typically covered in a single variable calculus course, it is quite technical, and it can be intimidating if you see this, very early on in your undergraduate math career. We are not, as most textbooks, going to spend too much time on this definition I'm about to talk to you about. Instead, we're going to focus on the intuition behind this definition, and then we're going to spend much more time showing that limits don't exist. than spending time showing that limits do exist and calculating them. Okay, all that being said, let's go through this definition. What does it say? Suppose I have a function with a certain domain, D, and suppose that D contains points arbitrarily close to the point AB. Already you can see some of the challenges in thinking about this definition, but I'll keep going. We then say that the limit of f of xy as the point xy approaches the point AB equals L if, and here comes the big if, the distance between f of xy and L can be made arbitrarily small by making the distance between xy and AB, where xy is required to always be in D, the domain up here, sufficiently small but not equal to 0. And then, the usual caveat, an analogous definition holds for functions at 3 variables. So there's a lot going on in this definition. So what I'm going to do is I'm going to draw you a picture. And the picture is going to be of a sequence of images to show you what it would look like if, in fact, we had a function. Oops, excuse me. Let's see if we can get back here. Oh, almost perfect. If indeed we had a function where the limit was indeed equal to some number L and did exist. So let me draw you that sequence of pictures. First thing I'm going to do is I'm going to draw my axes, x, y, z, and then I'm going to draw, some kind of curve here, some surface, and then I'm going to draw my points a comma b here, and let's call the y value that or the z value that it corresponds to, let's just call that f of ab. And certainly we are going for the case where we have continuity, which we'll talk about in the next video. So I'm trying to associate f of ab with L and kind of jump to that simpler case. Okay, so what am I going to do? I'm going to duplicate this to show you what this definition is really talking about. I'm going to duplicate it twice. So let's move this over here, and then let's also move it one more time. Great. All right, so what's this definition saying? So we are saying that suppose, removing all this clutter up here, I have a domain D. Sure, that's usual simple assumption. And then suppose D contains points arbitrarily close to the point AB. What we mean by that is we're not going to consider a domain D which is just a set of points that are far apart, and far apart from the point A comma B. This is a legitimate domain. We could consider functions on sets such as this, but we won't. And that's kind of the point of the definition. Considering such functions is usually done in a more advanced course called real analysis, which may follow this course in your trajectory through mathematics. So then we say that the limit equals L if, and here's where the if is, the distance between f of x, y, and L. So that distance occurs over here on the z-axis, because f of xy is a z-value and L is a z-value. So there's kind of some interval here that represents f of xy minus L. So that's a difference in z-values. So there we're looking at kind of like, if you think of this as a point on the surface, which is z equals f of xy, the blue surface here. If you think of this as a point on the surface that's higher than this one, then we're thinking about all the z values in between. Okay, so back to the definition. If that distance between f of xy and L can be made as small as you'd like by making the distance between xy and AB, where we're always in the domain, sufficiently small. What does that really mean? Here's what that really means. So suppose I take, just for the sake of keeping things simple, a disk around AB. Okay, that disk maps to a region over here. It might not be a disk anymore, on the surface z equals f of xy. Every single point on this disk is close to AB, and all those points, at least as I've drawn them, are mapping to somewhere close to f of AB, which I'm taking to be L. Suppose then in this second picture I make that disk even smaller. So this is kind of the idea that we had of a limit in the single variable case now being generalized. So that's a smaller disk. And what happens to those points? Well, at least the way I've drawn this nice surface, it seems like the disk should get a little smaller, right? These are the corresponding z-values of all of the green dots on the plane. And then in the third image, I make the disk really, really, really small, tiny. And that should map up in the surface to a really, really small disk. So it's in this sense that this definition up here is operating. You are making the distance between xy and AB, those are points in the plane. You're making the distance between all those points and AB smaller. You can do that by making these disks have smaller radii. And what you're looking for is if the distance between f of x, y, and L shrinks. And that's kind of what's happening over here in the red circles, right? All of these are points on the function. They're f of x, y points. And as I make this red circle smaller, these points get closer to the middle points, which for us is f of ab equals L. So this is as much as I want to say about the existence of limits and the intuition about what's happening. Because as I said, calculating limits and showing that they're actually equal to certain numbers, to a number, evaluating limits in this multivariable case is very tricky, especially from this definition. I will say one last thing. So lots of properties of limits carry over from Calculus 1. So you might have learned, for example, the limit laws that tell you that, for example, the limit of a sum or difference of two functions is the sum or difference of the limits, provided each one of these limits exists. Those collectively, there's a bunch of them we refer to in Calculus 1 as the limit laws. Very similar limit laws apply and carry over to the multivariable setting. That doesn't exactly help us in this video because the presumption is, excuse me, that you know that these individual limits exist. And we have this kind of cumbersome definition to evaluate those. But again, this is just to say that things have gotten more complicated. Some things change, like up here, this definition. Some things stay the same. So there is some comfort in knowing that the same limit laws carry over. As I said earlier, what is much easier to do is to show that limits don't exist in the multivariable context. So let me show you why. The reason has to do with this, just even the intuition we've developed about what this means already. So if I'm going to claim that this is true, as we've already seen, I'm making a very strong claim. I'm making the claim that if I look in the plane, wherever the point AB is, and I stay within the domain of F. Let's say that the domain of F is this set here, D. Then I'm making a very strong claim to say that the limit actually equals L. I am saying that whatever path to AB I take inside this domain, however curvy, however crazy, along each of those paths, I eventually get z values that are getting as close as I'd like to L. So that means that this has to, if this is true, this has to be true for every path that can eventually end up at the point AB. That means that if I can find even two paths that make it so that I do not end up, see if I can erase some of these paths. Let's say I find these two paths. And I find that along this path over here, I tend to some value L1. And then along this path over here, I tend to some value L2. And I find that L1 is not equal to L2. Then I will be done. Then we'd conclude that the limit does not exist. Okay? Because again, this is a very strong condition. It says along every single path, the limit, the z values have to tend to L. So if I find even two paths along which the z-values don't tend to the same number, then I know that the limit doesn't exist. I can also find, not tending to the same number could be in the calculus sense. It could also be not tending to a number. So maybe it goes to infinity. F of xy goes to infinity as you approach AB along a certain path. So I've put that information here so that we can reference it later. So the title is very illuminating. Obtaining different L's along different paths implies limit does not exist. So suppose C1 and C2 are two paths leading to AB. If you are able to calculate, and we'll do this in a minute, that the limit is L1 by following the first path, and then you're able to calculate the limit is L2 by following the second path, and these two are not equal, then the limit does not exist. So what I want to do is give you a very, very quick example and then show you graphically how this works, and then walk through an example that is analytical. So do this without the graph, the aid of a graph, at least at the beginning. So let's consider the example limit as xy goes to 0, 0 of the function x squared minus y squared over x squared plus y squared. Okay, so I'm not going to do it analytically. I'm not going to try to actually evaluate this limit using algebraic techniques or any of that. I'm just going to show you the graph of this function, and I'm going to show you why up here this is true. I'm going to find two paths, C1 and C2, along which the function's values tend to different numbers as we approach the same point, 0, 0. So let's do that. So I'm going to switch over here. And the first caveat that I'll mention is the usual one. This calcplot 3D is fantastic, but like all numerical plotters, it has trouble when we divide by very tiny numbers, or when we approach asymptotes or take square roots of tiny numbers. That is what's going to be happening here, right? So x squared plus y squared is in the denominator. And over here, as we get closer to the origin, we're dividing by 0. And it's even worse because the numerator is also becoming 0. So this poor computer program, we are forcing it to calculate something like 0 over 0. Obviously, that's not calculable, but the numerator is going to 0, the denominator is going to 0 as we approach the origin. So, applet is understandably having trouble dealing with that. Nonetheless, let me pan around so you get a sense of what this surface looks like. It's actually quite nice and smooth, except for at the origin, right? So we are going to figure out what's going on there in a minute. Part of the way I'm going to do that is I'm going to ask you to keep your eye up here on the values of the function, okay? And so then I'm going to go over here and click on this, and then that's going to pop up for us. There you go. Over here, I can change the x and y values, and then keep your eye here for the z values, and then also glance over here every once in a while to see where the z value is on the function. So notice that I am going to leave y equals 0. So I'm just going to travel. I'm going to change x and leave y equals 0. So this is decreasing y. Y equals 0 is the xz plane. So you can see this blue dots. Basically, it's going to move around the top of the function this way and then this way. Once we get close to 0, this is where the limitations of the program, you'll see that'll be apparent. But okay, so I'm going to go here and I'm going to start at an x value that's way over there. So around x equals -2. You see on the right-hand side, as I move toward the origin, I'm just moving on the top edge of this function. And then if you're looking at the y values at the very top of the screen, they're all equal to 1. And then at x equals 0, this applet has a problem. It claims that the function's value is 0. But, the denominator is x squared plus y squared. When you substitute x and y both 0, you get 0. We can't divide by 0. So that's the issue that the applet is having. But anyway, at every other non-0 value for x and y, the y values, I think, are correct. And you can see at the top here, the y value remains 1. No matter what x value I am using, as long as I keep y equals 0. So now I'm doing something very similar, but instead I am going to set x equal to 0, and I'm going to travel along the changing y values. So I'm going to travel along the y-axis. So let me rotate the graph. I'm going to rotate the graph here so you can see the bottom part of what's going on. So now I'm traveling along. You see that bottom part that's kind of straight? That's what I'm going to, this bottom part here kind of straight, that's what I'm going to travel along as I change the y value. So now keep your eye on the function values at the top of the screen. They're all equal to -1. Again, there's an issue here when I get to 0, 0. The function's value is definitely not 0. It's undefined there. But for all the other values, the function's values are correct. They are -1. So what are we seeing? We're seeing that if I approach the origin along the y-axis, from the top and bottom directions, the function's values are -1. However, if I approach the origin 0, 0 along the x-axis, doesn't matter what direction I'm going in, the function's values are 1. So that tells me that I have an issue. If I go back to my gray takeaway box here, I have now found paths C1 and C2 along which if I try to evaluate the limit, then I get different function values, -1 and 1. So this limit does not exist. Okay. How would we show this analytically? How would we actually show this? And especially on a quiz or an exam, we don't have a technology with us. How would we figure this out? So let me do that by finishing up with this example. One of the best ways to do that, and I'll just mention quickly, this is a very similar function. It's not exactly the same, but I'll do this example first, and then we'll go back to the one we just did. One of the best ways to show that a limit does not exist, again, we're using this approach here of finding two paths where it does not yield the same function value, is to start with simple paths, right? So it's what I did in the applet right now. So how about first we try x equals 0. So let's try approaching the origin in this limit, which is, this is where we want to head to. Let's try approaching the origin along the line x equals 0. So if I do that, then I will still have to approach 0 for y. But here in the function, if I put x equals 0, I get 2y squared over y squared. And that is going to always be 2. Because remember, now we're back to single variable limits. That's why I wanted to review it at the beginning of the video. Y squared over y squared, this cancels so long as y is not equal to 0. But we're taking a limit. So y is never equal to 0 in the limit, right? We approach indefinitely in limits. So in fact, this limit is 2. Now we're going to try a different path. So what if we try approaching the origin in this limit, which is what we want to do, along the line y equals 0? Well, if I go back to here, well, I'm approaching along y equals 0. I still also need to make x equals 0 to make xy equal to 0, 0. If I go back to the function here and I set y equal to 0, I am calculating this limit. Similarly to before, right? X squared over x squared is 1, so long as x is not 0. It isn't because we're calculating a limit, so I get 1. We can see here, if I were to draw this graphically, right? If this is the plane, then what have we shown in number 1? X equals 0 is the y-axis. So we have shown that, so here's the points we want to eventually find the limit at. We have shown that if I approach along the y-axis, the y value that I get, the limit that I get, is 2. And we also showed over here that if I approach along y equals 0, which is the x-axis, if I approach using these paths, the limit I get is 1. So these two L values are not equal, so we conclude that the limit does not exist. That limit does not exist. Okay, and as promised, let me go back then to the example we were just working on and do the same thing here. The same approach works here. So along x equals 0, we are, again, approaching the origin in this limit, so we would be left wanting y to approach 0. If I try x equals 0 here, I get negative y squared over y squared. There's that negative 1 that we were seeing in the applet. Along y equals 0, I still need to approach the origin, so I would need to make x go to 0. If I put in y equals 0 here, I get x squared over x squared. There's that 1 that we kept seeing from the function values in the applet. These two are not equal, so same conclusion from before, limit does not exist. Okay, so quick recap. If I go back to the first page, some stuff stays the same. So the general notion of limits caring about direction, right? We want the left and right limits to be the same and to exist in order for this overall limit to be the same. That's single variable calculus. Similar thing is happening here, except that it gets much stronger. So that is this definition. As I mentioned before, I'd like you to sort of understand this picture, but I'm not going to ask you to deeply understand it, because it effectively, calculating the limit with this picture goes back to a method of limit evaluation that is not so often taught in the usual Calculus 1 course. Instead, what this definition implies is that if we say that the limit exists, we're saying something very strong, which is that no matter which path you take to get to point AB, you always tend to the same value L for the function. And from that, we can extract what is useful and is very doable, which is trying to find paths along which the limits are different. So that leads to this gray box. So that's really the takeaway, second big takeaway, I guess, from this lesson. If you can find two paths leading to the same point that you're trying to evaluate the limit at, and you can determine that the function tends to different numbers, or maybe from one path it tends to a number, from the other path it goes to infinity, or from both sides it goes to some version of infinity, right? Lots of different options. Then you know that the limit doesn't exist. And then again, this is one of those times when definitely it would be a good idea to just try checking out CalcPlot3D and plotting your function to see get some insight into what's happening. Understanding, of course, that there are going to be limitations here. So especially if the function involves dividing by 0 or some other type of tricky operation for a computer to do, then you might have to use some of your math know-how to complement what the applet is trying to do near those points. Great, so that's it for this video. I'll see you in the next module.